right? So I have things that are on center points, right? So you want to make sure that you have, I start also in the grid system, so it's like kind of on the center there. I have a center point here, so that when I change this overall length, it doesn't just make this part longer, right? It centers it, right? So you can easily change this, and notice there's no dimensions on the bottom because I'm making it symmetric. So I just make this line equal to that line, right? So if I want to make this 16, the whole thing's going to update nice for me, right? So you don't want to be chasing your tail on the sketch, especially if you're using like solid mesh and you got to iterate. These are the numbers you're going to want to iterate on, right? So I start with a sketch, and oh, did it change it? Actually, did change it. I start with the sketch, and then I extruded it to the dimensions I just showed. Okay, so now I want to apply a load, right? But I want a center point here, right? So you can do a point, which is in this reference geometry. You do point, and then you select this face. You can do center of face, and it puts a point in the center of the face. Okay. Now I should make this a little bit interactive, but I'm gonna ask you guys stuff, but I'm gonna go a little faster. I was gonna see how you guys want to load this, but for now, let's just put a point here. There's other ways you could try to put this on. So some of this I might even do purposely wrong just to show you other features that how you could do things. So I had that point there, so I'm gonna unsuppress it. Okay, that's enough. That's enough to run it. So I'm going to simulation, and I'm going to do a new study. Is this cut off? Okay. I'm doing a new study. And you can see my last one I was doing frequency. So, oh, this is the name. So I'm going to do static. And this is where you should do like a decent description, right? I'm doing, the solid mesh, it depends on what you think is going to change, center point load, something like that, right? Depends on what you think might be your next iteration, but name it something besides static study 1. And I'm going to open up a spreadsheet real quick because I want to write this down so we can see if things are converging. So this won't be as nice as you'll want it to be at some point, but that's my study's name. Okay. Okay, and that's all I really need, I think, to start. Oh, you can have commas. Okay. Okay, so you guys can see that, right? Okay. All right, so you can see I'm going to do a if I just do a mesh. So they have this other thing called like mesh advisor. And I don't necessarily want this to be a step-by-step thing. I just want to see some results. But this actually does kind of make you think about things. If you use there's a load advisor, there's a boundary condition advisor. So you can actually use the advisor if you're new to it to figure out what you have to do to run it. So you'll notice here, I can choose to treat this as a beam, or I can also make it do a shell manager, except I don't have any surfaces to use as shells. It'll let you select it here, but right now I'm just going to do a solid mesh. Oh, okay. So you see this has fillets, right? So it's like, okay, what do we say? We want to go back and not have fillets, right? So there's this thing called analysis prep. So analysis preparation, and there's a area that says simplify. There's a button that says simplify, and you can remove all fillets, all chamfers, all holes, right? And so I can find now, and it finds this fillet for me, okay? Now, if I had drawn that in the sketch, it wouldn't have found that for me, right? If I had drawn a hole in a sketch, it wouldn't have found it. It's looking for features. So it finds it for you, and then you can suppress it. So I want to suppress it so I don't have that fillet. You could also have just done that. All it does is actually go into your CAD and suppress it. So you could just manually suppress it. But if you have 50 fillets, it's nice to just do this, right? And it'll find all of them. I don't know why it's it took me out of simulation. Okay. So I'm going to, you can do this, depends if you're applying like forces to, I think in solid mesh, you can put the mesh in any order. You can mesh first or put loads and boundaries on. So let's put on our boundary condition, okay? Oh, thanks. I don't know why I did that. I might have closed it and not accepted it. Thanks. Okay, so fixtures, right? So this is where I think it's weird. You pick anything and then you can change it later, right? So remember we have a pinned condition, right? So what should I do, right? I mean, remember this is a solid mesh. So if I do advanced and I use my reference geometry, it's only letting me pick translations down here. It stops there, right? So I can also pick, you might think, oh, I want to do a fixed hinge, right? But that only applies to cylindrical surfaces. So I can't make this face a hinge because it's going to give me a warning that it's not a cylindrical face, okay? So you have to manually make this basically a hinge, right? A pivot joint. So let's, we can do this several ways. I'm just going to pick the bottom edge here and fix it, right? Remember, fixing it is only changing the translations. So it's going to act like a, again, this doesn't mean it's the right way to do this. This is how I'm coming up with it in the moment. So I can do fixed geometry. You can see if I do the face, it's doing everything. But if I do this, it's going to do that edge. And you want to do both edges. So you can do them all at the same time. You have to be careful if you picked an axis that if like this face has an opposite, angle, you might have to do it separately. If you have constraints in different directions, make sure you know which vector it is. Okay, so I fixed it. Now I got to apply a load. So I have an external load, force. Oh, did it hide my point? So there's my point. Remember, this is where you can get a weird thing if you don't change the units first. So if I put 100, I said, oh, I actually wanted this in pounds. I go to pounds, it actually changed it to 22. Okay. So you have to go back and change it back to 100. I think that's what I had. Yeah. And right now it's picking this direction. So you want to pick select direction. That is picking the wrong thing. And I can just select like this edge. And then you can do reverse direction. So there's my force down. Okay. All right, now that's it. I mean, we're gonna mesh. So just do a create mesh. Don't ever do just mesh and run, because you're gonna waste time. You can start in the middle. I like to start a little coarser. Okay, there's my mesh. You can see it only has one element through the thickness of these things, right? Okay, is that a good mesh? And we don't know, right? So if you go right, I think you do details, and this tells me, if you guys can read this, it says mesh quality high percent. So mesh quality, I don't know how it does this mesh quality high, what that actually means. So my percentage of elements with aspect ratio less than 3 is only 44%. Right, it doesn't really look like a good mesh. So I'm actually gonna like mesh it a little bit finer. I don't want to go too crazy because I want to actually show you guys convergence. So I'm just going to do one more. It's a little bit smaller. Smaller doesn't always mean you're going to get higher quality meshes either. So it went up to 45, right? It went up a little bit. Okay, I'm just going to run this so we get some results here. Oh, I need to apply material, right? So if I just run it, it's going to say material not defined. So then you can right click. You can also do this if you do it in CAD. When you're modeling it, it'll apply the material. So just make sure if you forgot to apply it here and you started it off as some other random material, you might forgot. So I'm going to do aluminum. We said it was 60, the typical. All right, that should be enough to run it. Okay, so here's my results. So it's saying, here's my von Mises stress. Oh, I want to change. So there's a lot of options when you get in here. Yeah, I want to edit the definition. So I want this to be in PSI. That's how we were solving everything. Okay, so let me see PSI.
Oh, it went back to 1 for some reason on the force.
Is that why? Yeah, see, I was like, this looks like too low of a stress. See, there you go. I mean, that's a sanity check, right? My stress was 0.2, right? So I don't know why I did that. So I've run into problems with this thing.
I think when you went from normal to selected direction, it like re-updated the force for some reason.
It's like not letting me change it. Sometimes you have to go back in. Yeah, it's like I think it's a bug. So I have to go back in several times. Okay. So there you go. Right away, I knew something was wrong, and I didn't know why. Luckily caught it. So now let's rerun it because the stress seemed way too low. All right, there we go. So we get 90 psi. So does this look? I mean, does anything look weird on this model? So it looks like it's acting like it's pinned, right? We can activate the displacement and animate it, right? Looks like it's acting like a pin beam, right? Pretty good. You can slow things down. This is where you can save as an AFI file and make a, if you do that, you have to save it and then click play again, and then it saves it as a file, and then you can embed it in your PowerPoint and change the speed and all that. Okay, so let's just write this down. Deflection, I think I want in inches too. So so we're going to pull up the, I'm just going to do it on my screen. So we have like a single point. Let's do deflection in inches, and then so who thinks this is right? You think it's right? Okay, stress and PSI. Okay, so once I have this set up, so we have 0.002669 inches, and our stress, this was von Mises. Was 90. Okay, what's the next thing we should do? Anyone? let's change our, well, first you should look at this a little closer, right? I mean, what's going on here? Like, where's our, so when you look at the stresses, you're going to want to tell it to show max annotation, sometimes even show min, which would be like a compressive stress. So, oh, it's giving me a max over here. Is that where we expect the max stress to be in a beam with a pin joint? Right? So there's some weird stress concentration going on here.
It's a free surface, right? So.
Yeah, so what else you can do is, again, this isn't the way I would solve this problem, so that's why it's, you know, giving you weird results. Let's just refine the mesh. So you just create mesh again. It says it's going to delete these results. This is why you need to have a spreadsheet, right? So I already captured this. Or you could copy this and do a new one. Let's just go a little bit fine. Okay, and then you can, you can check your, oh, look at this. We went to 98% from 45%. Okay, so we have a much better, nothing over 10. This is like a really good mesh. So I would use this mesh. And I would basically throw all those old results. Let's just see what happens now. So look, the max moved, right? That shouldn't be, we didn't change anything, right? All we did was change the mesh size. There's no reason why the stress, the peak stress should be somewhere else, right? But now it's where we think it should be, right? It should be at the center of the beam. And this stress is still a little bit probably artificially high, but so if all I did was, this is a good example, in my spreadsheet, I said we had a single point load. I'm not going to get too crazy with this. I just want to make sure we track it. And then let's call this run 1, and then like run 2, finer mesh, right? Something like that. If I just wrote the new stress down, it wouldn't tell me anything, right? I mean, you would have a, so if I wrote, what, 224? Okay, if I wrote that, it's not enough information, right? You'd have to put, at pin constraint, something like that, right? And now at load point, right? So your stress changed, right? So you can put detailed notes in here when you do it. Let's see what the deflection is. I think I just want to run one more solid mesh and we'll switch over to the plates. The deflection didn't change too much. So you notice the deflection didn't really change too much, right? Compared to the stress, right? That's a big difference in stress. But that's because I was looking at the mesh wasn't proper. So what else looks weird about this? I mean, is this how we think the I-beam is going to fail? There's going to be this huge dent in the middle, right? It's a limitation of solid meshing, right? It's like, okay, this is really distributed over the I-beam. If you think of putting like, some lead weight on the I-beam there, it's not going to poke a hole in. And I bet if we, I'm not going to write this one down. I bet if we went finer, Like if you know anything, if you didn't take statics or strength of materials, mostly statics, you probably would have thought the high stress point would be at that restraint, right? I mean, you might run it once and you would have got that result, right? And that's not where the high stress point should be. It doesn't mean FEA is wrong. It means your model is set up wrong. So we did a little bit finer mesh, just for moving faster. I'm not going to check the mesh quality, but it'll be similar to the other one. And now I'm at 240. So it seemed to converge decently. I mean, I would, oh yeah, so not quite, right? It's at 240. So that's probably, I would keep running this. And I bet you, because it's that point load, that this is going to just run away from us. And you're not going to see convergence before you get to the finest SolidWorks offers you, right? And then you can go into mesh control and whatnot to get finer. So here you can do apply mesh control. It's better to not see it. Oh, I'm just trying to undeform it. But. So you can select entities. Now remember, it's put back. So I could say on this, I want to dial up, you know, the mesh size, and you can override. This thing only goes so far. You could type in the mesh, like the element size you want. And so you could do this on certain features. You can make, so let's just do this real quick. Let me make this whole face super fine. Let's do that. And then I'm actually playing around here because I've tried this. And then if we do a Crepe Mesh and we keep it coarse, it should keep this face as a fine mesh. So see how fine this mesh is here, right? It's super dense. But then everything else is back to the coarse, right? So if there's an area of interest, you could just refine that area. We could have done that in that first case where we had high stress here, you know, at one of these places. And it still has a decent amount of elements, 93%, over 90%. So this would have been a good mesh. But you know, the downside of this thing is this. We re-erase the results. Is this point load? So there's other ways to do it. Let's just try one thing, just so you guys know it exists. You can split. Let's see, I think I did this before. So what if we just split this face, split this into a different face, right? So now you can apply the force here, and then you can extrude. You can even, you know, you can make something like this to apply the load, right? So let's go back to here. So the other thing you can do, by the way, so then you can, I lost the results, but you can copy this over. So copy study. So I would recommend doing that before changing everything. So you copy the study once you have good result, you know, decent results, and then it tells you where it came from. So it came from the solid mesh. So you could just change this. You know, I'm just gonna say boss feature, something like that. So it copies the constraints, it copies the loads, and all that over. So now we're gonna keep the constraints. We're gonna change the force. Instead of that point, we're gonna just do it on this whole face. Okay, that's 100 pounds total across that face. Now what I'm gonna do is I'm gonna make this a super stiff material. I think I did this. I have custom materials here. So here I called it stiff metal. So what I did was I added 2 zeros to the modulus. Okay. I used aluminum or steel or something, and then did custom. You can do that in SolidWorks. And all I did was change the modulus. So it's 100 times stiffer than steel, and just that part. So that's, you can see here, this is called stiff metal. This is 6061. Oh, I do have the mesh control on here, so I can delete this mesh control. And then I'm going to create the mesh. I'm going to try and keep it similar to the last results we had that were good, which I think was like right here. Okay, and again, I don't really care about any parts in here, right? I don't care about the stress on that part, and it shouldn't really be too stressed. I'm going to run it. Oh, so you have to bond these two parts together. There's two bodies. Where is it? I don't know why it's not letting me do it. I think it's frozen. Oh, sorry. I have a thing on my other. I have a warning on my other window. That's why. Oh, don't tell me that you just crashed. So I crashed SolidWorks. Oh, but my error report was set successfully, so that's good. Sorry, guys and girls. So yeah, you need a bond. You need to have it like bond those together because you made them two separate. You could have when I did that extrusion, what's important to know is I didn't merge the bodies, so I just did extruded by itself. I might have recovered it. I guess I should be saving this as I go. Okay. We're not in too bad of a situation. We got it recovered. Okay. So connections, there you go. It's a it usually does it by itself, but oh, here you go. You can do automatic and select the two components, find contact sets. So the two is the face, is finding the purple face and the blue face. And it creates basically a rigid contact between them. Let me see if this works. Okay, it's running. You can see how long it takes, relatively speaking, when we do like another model to solve this. I'll try and finish the next two in 30 minutes. This is the hardest and longest one to do. In fact, I might skip the plate ones if you guys want. Okay, so I'm getting warnings about check model boundary conditions. So maybe this is a good example to do a let's run a modal analysis. So something went wrong. I don't know what went wrong. I actually don't know what went wrong. So I'm going to do a new study. And I'm going to do frequency. I think this is useful because I think you guys probably haven't seen modal analysis before. So I kept my global contact, which is good. Actually, I created a different one, it looks like. This might have been the better one. But let's do an example where I'm going to under-constrain this, okay? So I don't need loads, remember. It's a modal analysis. So I'm going to do fixed geometry. And this is where I said, I'm going to do this line, right? I'm telling, what I said earlier is this thing can probably rotate. It's supposed to be able to rotate about that line, even though you called it fixed. So I'm just going to do that. I'm just going to mesh it. This seems to be a decent mesh size. And I'm just going to run it. Okay, I have to do the material again. The material actually doesn't matter for this as far as finding zero modes. Your actual real first mode will change if you have different material. And then this one, I'm going to apply my stiff material. And we'll run this. I wish this window kept stayed on the other one. Okay, so here's my modes. So you can see up here, mode shape, I have a zero hertz. The only way you can see this better is if you edit this definition. It tells me I have 0 hertz. And then my second mode is 400 hertz, okay? So here's 400. This one actually has straight up 0, right? So there's 1 degree of freedom that's not constrained. And so if you activate this mode, if you animate it, animate. That's the degree of freedom, right? It's pivoting about this point, right? Which is what we wanted to do. We just didn't pivot the other end, right? And so, but if you thought this was fixed, you wouldn't see this space moving at all, right? So this tells me, oh, I'm under constraint. I can rotate about this, okay? Okay, I think I'm done with this. I had other things to show, but I think I want to speed up probably. The other thing I'll just show you in the CAD world. Oh, do we want to run? Yeah, it's not running, so I'm not sure exactly why that one's not running. But you'll get a different result doing this way. And
one more time, maybe it was the bonded.
I think it was. Because this says I don't want this. I want this to be the bonded one. Oh, okay. There we go. So if I ran modal, yeah, surprisingly, it fixed it automatically when I went to the other one, but it would have probably showed that one sitting there by itself, right? You'd see that. You'd actually get 12, or you'd get 7 0 hertz modes. You would have got that pivot one, and you would have got 6 0 hertz mode from this guy, not constrained anything. Okay? So that actually would have solved it if it didn't fix it automatically for me. So I need a remesh. I mean, you can see how iterating on solid mesh, solid geometry can take a while, right? All right. So now I ran. So let me look at my displacement. Yeah, my displacement didn't really change. So now we can go to this. It's almost exactly the same. Yeah, I remember that was just a finer mesh. Okay, and then we did rigid, you know, cross member or something like that, or rigid extrude. And yeah, 283 is basically the same, right? And let's check out the stress. It went to 128, and look where the stress went. It's here, which we don't care about this part, right? I mean, this is just where it's loaded, but it got rid of the stress concentration on the part we care about, moved it here, and now it's loading the I-beam, which looks a little bit more like the way you would expect the I-beam to be loaded, right? So let's write this. So what you should do, like you can write, again, I'm doing this kind of sloppy. You can format this a lot better. This was like 129. And by the way, I always put units, so in Excel, right? So this is the column for units. You never know when your models changes, and you want to make sure. And then you can also say it's at, you know, extrusion, and then you can say what the actual stress is. So now let's get into probing around. So now you have this stress, and you want to, let's see, where is it? Probe. There's a probe button here. So, oh, before I do that, so notice how it doesn't show you the mesh. I think you can do show mesh. This is where I said, oh, there's an option to, and when you do edit definition, these other things show up too. So this actually shows, this is when it says blending versus not blending and stuff like that. This is where I want to show the mesh, not the model. Okay, so my boundary options is mesh. So now I can see where the stresses are on the mesh. And you'll see why that's useful. So this actually is a decent way to load it, in my opinion. So now I'm going to probe this, because I don't care about that. I expect and the probe's going to be underformed. I'm going to actually pick, like, you can pick different nodes to see what the actual stress is there, okay? So I'm going to pick something where I think, you know, I don't know what it picked there. Let's just use this as an example. So this is more realistic, probably. So 45 psi, okay, in the part I care about. Oops. By the way, I don't put units in there because you might want to scale it later and use formulas, and so you want it to be just a number, you know. I'm gonna call it a day on the I-beam on the solid mesh. So you want to be explicit about it. Okay, so let's call this done, and then you want to like merge this as, you know, one line item basically that you ran. Okay. What else I want to show you here? I took some notes on things I can show you. Oh, we can check out the design inside here. So this might not, yeah, here's just do a couple things. So this might not be super useful because you have a super high stress here and everything else looks blue, right? And so you're like, well, I just care about the stress in the I-beam. There might actually be a way to ignore that body, but you can edit the definition. And then in the chart options, instead of automatically define the max value, I just cared about things that are like 50. Let's see if it lets me do this because I have a number that's higher than that. So anything above that is just going to be pure red. 50 to like 10. So remember how the whole I-beam was blue before? It looked like there's no stresses in it. Well, now I'm getting, you know, I knew there was 40 something PSI. So now I can actually see the stress distribution in the beam that I care about. Okay, so I changed the plot contours. So that looks, you know, decent. And then you can do, actually, I don't know where the design, so you can add different plots. You can do strain plots. You can change the stresses. So if you want to do a, define a stress plot, you can change this to normal stress, right? X normal, Y normal, Z normal, first principle stresses, right? And if you're a little rusty or haven't even learned these yet, in the backup, I actually have I have this to remind yourself of what these first principle, second principle stresses are that you can pull out of SolidWorks. Okay. Okay, so let's put in the results here. I'm going to say 42 psi, I think, in the I-beam. 45 is our final result, and by the way, when you do present stuff too, don't put 9 decimal places in your results, because first of all, it implies you think that the analysis is to that precision, right? So cut things. I mean, deflections are a little weird, different, right? I would probably write this in micro inches or something like that, or thou or something, or I would cut it off after the 8 if I was presenting this, and I would do maybe 1 decimal on the stress. Okay, so let's call this one done. Let me just find the design insight. Right here, design insight. So here I can manage it's real sensitive, I guess, in this model because of the high peak stress. But you can drag this. It might be because of my settings too. Anyway, you saw the picture of it. You can drag that. I think since we have a high stress concentration here, it's not working as smooth, and you can see where you have high stress and low stress kind of. But, okay, let's move on. Maybe I should just do a beam instead of the plates. Let me just show you the modeling for plates. I think I have it suppressed. So I'm not going to walk through analysis this way, but so for the beam, there's also a way to do this where you split. So the other way to do this is to put a load on this entire face, on an internal face, right? So here I split the body. So I split this body in half. And then you eventually have to split a bunch of things. Because I wanted just the web to be loaded. So instead of putting the flanges and everything, I basically split all these faces to where I can just load the flange. So you can do stuff like this, which just shows how hard it is to get a solid mesh to run, right? So you can see I separated the web from the flange. Anyway, so you can do that and create more faces basically to put loads there. Okay. Now remember, we probed around to actually find the real stress. If you just looked at the peak stress on that last model, it would have been order of magnitude higher, right? Okay, let's move on to, let me just open up I'm just going to show you the CAD modeling for the plate solid mesh, the plate elements. I think you guys, I suspect you won't use them as much as either 1D or 3D. But I do want to show you, since you probably won't see them that much, I do want to show you like an example. I'm I-beam plate. Oh, this is it. I-beam plate mesh. Okay, so you start with this, and then so this is if we were doing the solid mesh. So you need to make a mid surface, right? So you can do. I think there's actually analysis mid surface. So up here it says mid surfaces. You click mid surface and you select like the faces, the two faces. You select like the two faces you want, and it creates a mid surface between them. So that's what you're going to use to mesh. You're not going to use the thickness of any of this. So I went ahead and did that for all these surfaces. Keeps giving me warnings on this other page. Okay, so you do all these mid surfaces. Oh, I was going to unsuppress all these. Okay. So you can't see them because they're in the middle there, right? But I got all these mid surfaces, right? And now I need to extend, so I can actually hide this. So there's my surfaces, right? I mean, you can see there's a gap, right? Because when I did the gap there, so you want to extend the surface. So now I extended that up to there. You extend the other surface. Maybe I'll go something. So now it's down there. And then again, we have to put a point on that face, right? So that's the point we're going to load it. Let's see if we can do this quick. I'll run it. Let's just compare it to the beam. So we're going to run this study, static. It creates the bonded contacts already. Let's do the fixture. Let's see. Let's do the mesh. Oh, let me make sure it's a shell. So solid body. So you want to exclude from analysis the solid body. Okay, you're not using the solid body. You don't want it to solid mesh it. So even though it's hidden, it's actually still there, right? So you want to exclude from analysis. And now look, these are, see, this says that it's a solid body. And this is telling you it's a shell. It's only a plane. So these pictures there mean it's a shell mesh. In fact, you could right click this and say shell manager and actually make the solid body a shell. So you didn't have to necessarily go do this. You could do the mid surfaces in this part of it, but it's a little harder to control, I think, because you have to extend surfaces and all that. I like to do it in the CAD. So it says no thickness defined, okay? So you go to shell manager and it's gonna show the 3 surfaces, okay? So there's the thickness. I don't know why I did that. I'm trying to. You can. I think you can choose. There's a way. I thought there's a way to choose the thickness right here. So there's thin and thick. Remember, thin and thick is like having a beam. It depends on the aspect ratio. So if you go back to that chart I had thin shells and thick shells are basically beams. So mid-surface. So you can change a bunch of things in here. So let's just keep it simple. So you can group things like the flanges, like you saw before, but I'm just gonna make it the thickness that I had in the example, which is 0.5. 0.5 for the flanges and 1 inch for the. I'm trying to enter a number. 0.5. That's the web, so 1 and 0.5. Now you can group these so you don't have to always do that. Same with the material. I'm purposely didn't do this ahead of time so you guys can kind of see the process. As you do manage groups, basically you can call this like the flange. And so I can make this the flange group, and oh, look at this, the units changed automatically, and make this 0.5. And then I can turn this into the flange group, and it changes the materials for me, so I don't have to select it. And then I need to select this material. At least it saves it. Okay, so there, that's how I defined it. So when you want to iterate this, you don't have to go back to your solid model. You just type in new numbers, and it gives you a totally different geometry. Oh, it did? Thanks. That's weird because it's part of the flange group.
I think it was when you actually changed it back to
This is ridiculous. Don't change the top one. Okay. Now, a good way to check, this would have been obvious, right, is to show the, so you can, let me mesh it first. I'm going to have to mesh it first. So Crepe Mesh, I'm going to do a simple one here. Are you guys still following along? Or is, I think the advantage will be when you see the 1D beam. So stick with me. That one's a lot quicker to do. So it matters if you have offset surfaces. It matters, I guess, which the colors tell you like what side it's extruding on. I think so. It's not mid surface. It matters. If it's mid surface, it doesn't matter. So it'll extrude down from the orange or something if it's not mid surface. So you would want to make sure that looked right. There's a way to show the to actually show the mesh, but it's not. Worry about it right now. So okay, so let's do the same thing where we're going to add a force. We'll just do the center point. I'm gonna change this first to pounds. It seems to be better that way. And I need to pick a direction. I don't know what's going on now. I mean, do normal for this phase. Oh, okay. I gotta do. I actually don't know why. Oh, that points on the mid surface. That's right. That's so you notice it didn't let me do it because it wasn't on the surface. That's what this other point is for. So I projected that point. That point was made on the I-beam, and now that point's on the surface. I did that on purpose to show you guys. So now I'm going to put this force on that point, and hopefully this is wrong. Let me just, okay, and see what happens. Oh, It was making me toggle that for some reason. Okay. Does not like changing this. Okay. And then the fixtures. So we're gonna see a little bit of a difference here, right? If I do, if I go to the advanced, you're gonna see all 6 degrees of freedom show up here, right? So what we want to do is do a similar to the beam. Let's select this surface. I don't know why it actually split my face in half, but I think it was the I-beam was there before. That was the thickness of the I-beam. And now the direction matters, right? So this is the direction. Use geometry. Oh. Yeah. So in that direction, I want 0 displays. Man, I actually don't know. This is not looking right. I'm gonna turn all these on. Let's see what happens.
Is that reference plane? Is that just usually how it references all the other directions?
Exactly.
All the other degrees
Yeah.
of freedom?
So it's basically letting me constrain. I don't want to do 3 of them then, right? It's actually I haven't seen this before. So what we can do is maybe just fix it. So I would have to do that 3 times for like all 3 directions of what it looks like to that. We can just do the fixed geometry. I actually want this immovable, right? If I do fixed, and it gives you a little picture here. You can see how it's not letting this bend, right? We want this. We want the translations. So I'm going to select this. There you go. See all 3 showed up. Okay. Okay, that's just like the I-beam problem we had, right? The first one we had. I think we can run this now. Oh, wait, SS. Oh, it ran it. Okay.
And it's like not in linear elastic, it was in like plastic.
Oh, okay. So I didn't set the right one, but then it switched over and ran it, looks like. Okay. So let's look at this, see how this compares. Okay, we're getting 65 psi, but look, we're getting a similar thing, right? I was kind of deflecting in there. So let's be smart about this and let's do a probe. And this is telling us 30 compared to the 65, right? So that's sort of where we had we picked for the I-beam, right? For the solid mesh, I mean. So does anyone have a guess at which one's right yet? So we had 65. This is all I'm going to show for this one. So we're going to move on to the last one. So now I'm going to say we did this is the shell mesh. Okay, I haven't checked the deflections yet. 60 psi, at load point. And then, what did I have? 40, or 30, 30.5. you know, near a load point. Okay, so we're kind of comparing the 45 to the 30. I mean, that's a big difference, right? In stress, right? I mean, this is 50% higher stress, the 45. So like, which one is right? You have the same exact geometry, right? Same exact material. You just did a solid mesh and you did a plate mesh and you get 50% higher stress. Which one than the other? Now we didn't check for convergence on this due to time, but okay, let's just run the last case. So
what is it on the bottom of the surface?
Fourteen. I don't know if I picked the, yeah, close enough to where the other one was. Let's check the deflection. So 26 instead of 28. Okay, so let's log this and move on to the last one, and then I'll show you guys which one's right. So 30.5. All right. Last one, which will be the quickest one. Let me hit close when I did the other one. So I'm going to save this and close it. Or I'll probably save it. At least I think we'll see time, because I don't think anyone else here is going to be running something today that they want me to check, but I can stay if we need to. So we're going to do the I-beam. I-beam beam mesh. Okay, here's my beam model. That's it. Okay. Now, I drew it in 2 lines because I knew I needed a center point for the load. Okay. So this will probably be a most useful part of the whole thing. So I pay you guys again that stuck around and finally get some use out of this. So you could have just used this model here. I think I still have it open. You could have used this model that I started tearing apart. If you right-click the solid body and did treat as beam, okay? So you could have turned this extrusion from a sketch into a beam. However, you'd get one big beam. So you should have split the body, which is pretty easy to do. You split the body and make it a beam. So you can work backwards and make it a beam. But I'm showing you how easy it can be to start from scratch knowing you want to use beams, okay? This is a weldment. So since I picked a random geometry, by the way, it's really hard to rotate this because it's a line. Like, it's not really solid geometry. And so when you go into weldments right here, and you make it a structural member, I actually saved saved that extrusion I did. I saved that sketch as a weldment, so I could just make it a weldment. So you can make custom weldments and put them in the library, and then you can just, you can call it formulas 035 tubing or something like that, or so you can make your own, and then you can copy and paste that sketch and like slightly tweak it and make it another weldment. So you can just, after that, just use the drop down and change things, right? So this was a weldment. There it is. I'm already ready to model it. I don't need to make a point or anything. So I'm gonna do the new study. So it already creates joints, right? It creates joints now automatically. But you can also, if it missed something, you can, I think, go back and make sure that there's a joint there. But it should automatically make a joint. So this is super easy now, right? I'm gonna, I don't know why it always says fixed geometry, but if you click it, you can change it after that. I want this to be pinned, right? I'm gonna do immovable. And now you just select the joints. Boom. I have a truly pinned beam now. It's not like we faked it on the solid mesh on the bottom surface, right? Now I want to put the load. God help me with the newtons. Okay. I'm going to select this. Oh, right here. You got to make sure it's on joints. You can still select, for some reason, let's just select faces and stuff, because you could have some beams and some not beams, I guess. So notice it picked joints. It's picking the joint. You do need a reference edge. It's freezing on me again. I think you still need a reference edge. Oh, this reference edge makes more sense. It's actually the direction you're going to apply the load. But you could also, oh, I lost it. But you could also just use, I think, the coordinate system. So we're going to do this edge, and we're going to say there's a force of 100 pounds. God, I don't know why. It does not like it. Okay, I'm going to say okay and edit it later. I don't see the force, so I'm lowering. Oh, there it is. It's on the joint. You can barely see when I do reverse direction. Now you can't. Hide it in that angle, it's there. So I think I can hide, I do need to apply materials. I'll hide the beam so you can see. Again, you don't need the beam, right? It just needs the geometry. It's not doing a solid mesh on the beam. Hopefully I didn't choose some nonlinear or linear. So yeah, let me. So here's a load on the joint. So it's actually backwards. I think, right? Yeah, actually it won't matter. In the other case, it would matter because we had like a bottom surface, right? So there you go. Okay, now I'm going to create the mesh, and don't freak out. It's not that shape, all right? And similarly, you can make denser elements. So if you want, but let's just try this. Okay, I think I can run it. Okay, that was, you couldn't tell before, but when I did the other mesh, I could see the percentages going up, and the window open and closed. So remember, there's no von Mises in the beams, right? It's doing the axial and bending, right? Because it's ignoring transverse shear and things like that, right? So, so it takes the max, basically just combines the upper bound of axial and bending. But it should give you the same result if it's not too short of a beam as von Mises would. And you edit this definition. Okay, 36.2. Right. So let's do and let's check the deflection, and then let's see which one's right.
Is this average across the cross section right now, or is it?
It's max.
It's picking the max.
And I'm saying it doesn't do it through the
cross-section.
thickness. I'll show you. Thanks for reminding me. I'll show you the. So the deflection is 0.04. So if you want to see through the thickness, you have to render the beam. So there's obviously a lot of stuff in here. There's a render beam option somewhere, which I haven't used before. Oh, maybe it's might be. Oh, maybe it's define. Right here, render beam profile. So you want to go back to, you have to create a new thing. So I'm doing the axial and bending and PSI. And now it does it through the thickness. It says it takes longer, right? So it's actually running the running more analyses. So I don't, yeah. So you can see the profile. And I mean, this is a good result, right? We have the same stress on the top and the bottom. It's just one's compression and one's tension, right? We didn't quite see that in the solid mesh, right? Okay, so let's see. Let's put this in the PowerPoint at 36.2. There it is. Okay. So which one of these is right? Anyone have a guess? Hey, that was a good one. None of these are right. That's true. Which one's closest to being right? How would you? Let's say this was your. You had a class, and the teacher said you have to show me the result that's most, close to the theoretical result, and your whole grade depended on it. How would you figure out which one was right? You would what? Average them? Hey, 100 p. I mean, it's as simple. This is a simple hand calc, right? So you just do the hand calc. So you should make spreadsheets that let you do simple hand calcs, and you'll reuse them over and over. So I did that for this example. Let me hide. And if you guys want, I can show you how to like optimize in Excel with these results. Okay, so here's the problem, right? Here that I set up. Here's their equations. You can just look up in the beam book, right? Where you can derive these by hand, right? Using singularity equations. And so if you haven't gone through, like I said, static strength of materials, you're not going to be able to do effective, because you're not going to know how to check this result, right? and here's the von Mises stresses. So I just did this, right? So, you know, I put in the load, the length, the A, the B, these are all the I-beam parameters. So these are inputs, right? There's a flange width, thickness, height. Later, I put the density and volume in to show you how to do optimization, if anyone wants to stick around. And then these are all calculated, right? So this is the shear and moment. Yeah, this is obviously the inertia of the flange. So to get that whole overall inertia, right, you have to do flange, you have to do the web, you have to do the parallel axis theorem, right? So the neutral axis, do the area, this is the beam area, and so the total beam inertia is 305, 304. So you can also go check this, right? Right, if I go evaluate, I think, section properties. Oh God, I split this. Let me open the one that's not. So that's the first thing you should do, because everything's going to be dependent on that number being right. Section properties. So here's the inertia about y, 304. Right, 304. That's the major axis. And that's what I got, 304. Okay. So you do that, and then you just solve for these other equations. Here's my deflection. Should have been 3.5. No axial stress. This is how, since it's a long beam, the shear stress is really small, right, compared to the bending stress. And so my von Mises stress is almost basically my bending stress, right? So I got, 36.5. And really, if you're treating it like a beam, you would just use basically the 36.2, right? So which of these is close to 36.2? I got lucky that this worked out in class, because I didn't know if they would show it. So that's how you would check it, right? You go, okay, the deflection was 3.5 in my calc, and this is 4, right? These deflections actually weren't terribly off, but that probably means it's just these stresses are local concentrations, and the deflection, it's still closer to this number, the 3.5 is closer to this. But I trust that beam element model, right? I mean, it's right on the hand calc, and it should be for something this simple.
Why do you think the bottom was so bad? I was expecting the top was near the applied force, but I was thinking the bottom would end up being close to our end answer. I was surprised how off it was 15. I was surprised how far off it is.
Yeah, I don't know. And most likely the constraint, because we have a constraint on the bottom. So it actually didn't go past the neutral axis, probably, because we constrained the bottom or something weird like that.
Pinned. It was kind of like actually holding up those edges.
Yeah, right. That's the hard part about a solid mesh, right? Is you're trying to constrain nodes that can have 3 degrees of freedom instead of the joint where it's a perfect joint simulation, right? So it's really hard to constrain and put loads on a solid mesh. Like it's pretty hard to do that properly. You can put things like I did, like rigid members in, and there's other ways to do it. But in SolidWorks, I see a lot of errors due to the solid mesh and bad elements and just the loads and the boundary conditions. So yeah, I mean, this is the hand calc summary. So you should always have this, some kind of check like that, right? So I would have confidence in building a whole frame using this beam model, right? Because I at least checked a simple version of it. So I could build a whole, Baja frame out of this I-beam model, and I would trust the results, pretty. I would still do all my checks and all these other things, but anyway, so I mean, that's it. We can play around more with that. People can go home. People can try stuff on their computer. I can show you some quick, like, iterative solver stuff in Excel, like in 10 minutes if you guys want.
I'm curious, what do you use at work? Or like, is there any good free software? Like,
For what?
SolidWorks that for like FEA. It seems kind of like probably clunky.
It's a little clunky. It's actually way better than when I was a student here. And they did, literally you had no option. It just like ran a solid mesh, and like you didn't have any mesh control, like the little, you couldn't do beams or surfaces. Like it was just solid mesh or nothing. And that was it was terrible. We use FEMAP, and FEMAP's just the FEA software that does the geometry and stuff, and then Nastran runs the analysis, right? Same with NX, actually. Nastran is actually running the analysis. It's Nastran's the solver. And so that's probably, I don't know what solver SolidWorks is using, but all this stuff you see when you're drawing meshes and all that, that's just to make an algebraic matrix that they give to a solver, and the solver is cranking that out, and then it's only giving you numbers, and then SolidWorks is interpreting those numbers into colors and shapes and stuff, deflections, right? So there's always a different solver, right? So FEMAP is like the modeling, and we use Nastran to run it. They're synced, but sometimes you just export the FEMAP, and then you open Nastran and you import it and you manually run it. And sometimes you don't even put it back in FEMAP. You just go look for your like max displacement in a table. But if you want to see it in geometry, you can put it back in. But most of us now use NX because that's what we have to use for flight hardware. So anything we launch has to be modeled in NX, but people could export it and run it in FEMAP and stuff. But now we use NX simulation, which is like super powerful, and it's like it's an awesome tool. No, it's like 60K for like a license, or for like to buy it, like that whole package, yeah. And they're not like SolidWorks where they give students free stuff. Yeah. They're mostly for like automotive and like actually industry people that build the same things over and over because they have a lot of cool features for like cars and stuff that you can do for modeling. But like store different types of door frames, so you can like Frankenstein a car together from kind of like the weldments, you know, like you store certain geometry, you can store certain types of doors and things like that. Yeah, but I use Excel a lot at work, more than MATLAB or anything like that. Yeah, I mean, I can show you just a quick thing if you guys want. It's up to whatever you guys want to do. I'm here to help you guys. So, I mean, we can just adjourn, or people that want to leave can leave. We can like look around more in SolidWorks and do some more of the simulation stuff. I mean, we can still do that, and I can show you some Excel, cool optimizer stuff. What do you guys want to do?
Yeah, I
You want to see that? Okay. All right. So let's say. So by the way, you have these results, and you know what the yield strength is of the material, right? This is where you could scale. Yeah. Yeah. Okay. It's where is it?
You don't need it.
Well, yeah, for this I don't need it, but it's
deflection. Did you bury it in there? Oh no, it's up there on the left.
It's somewhere here.
20 to the 7. 10 meg.
10. Yeah, it's 10. 10 MSI.
It's like aluminum.
Yeah. I mean, that is a material I use, so I put the material property in. So I made sure this matched the SolidWorks. That's the other thing is, right? You could get this from a textbook and then choose a material in SolidWorks, and SolidWorks assumed the modulus was like 9.9 instead of 10. You'll get slightly different answers, but and hold on, let me see where this
Big crystal sneak out. Have you ever seen good software for fatigue?
fatigue analysis? No, I don't think we even use software for that. Okay, so let's say, I don't know, I don't have a really good example set up, but let's just say we wanted to maximize your beam inertia. You want to get the biggest I, right? And keep your mass low, okay? And so it's like you have these parameters to play with, right? you could change A. Sorry, I mean, I don't have that here as a picture. But you can change the beam. Oh, this is these. Sorry, this. You can change the flange width, the width of the flange. You could change the height, the thickness of the flange. You could change the web thickness, or you could change the web height, right? I think most of us at this point know what you would change to optimize it, but let's say you didn't know. So there's this thing called Solver up here. By the way, it's an add-in, which just should come with all of it. So if you don't see it up here, you have to go to Tools, Add-in, and add the Solver. There's also another simple thing called Goal Seek, which I can show you. But okay, so you're going to set the objective. All right. So you can set this to a specific value. You can set it to to minimize it or to maximize it. So I want to minimize mass. Okay. So I'm going to minimize mass. So I'm going to click this, and I'm going to click this mass box, right? And again, this is why I do my units on a separate column, right? Now what cells are you going to change, right? So variable cells. So you can select a bunch of these. I want to change all of these. Okay. Go ahead and change any of these that you want, is what I'm telling it. Now I need to give it constraints. Okay. Because otherwise, to make mass 0, it's going to make all of these 0. In fact, maybe you might solve it like that. Boom. I don't know why this has a number. That's a little interesting, but oh, it's doing something over here. Oh, it gave, once it did 0, it gave me so many errors here. But anyway, so you don't want to do that. Okay. I actually overrode my thing, which was the warning it was telling me. Okay, so it saves your stuff, so it saved everything. So you want to add constraints, okay? So you want to minimize mass, but you need some geometry, right? So we can make these up, right? So I'm going to add a constraint. I'm going to say that the flange, right, has to be less than, 20 inches, okay? And I'm also going to say, I'm going to set a limit for it. The flange has to be, greater than 1 inch, okay? And then you just do that for all of these, right? What's your constraints? I'm just going to make random numbers here. Less than 10, what was that one? And then greater than, I'm just make everything greater than 1. Less than 10. I learned how to do this. Just set my fantasy football lineup. I have to mind the lineup. That's how I learned how to do this. For $5, I'll pick the perfect lineup for you guys.
That you lost someone to auto.
This was the weekly. This is the DraftKings. Greater than 1. So yeah, this stuff I kind of Googled and then started playing around with it. Okay, last one. I don't think I did this one yet. Less than 10. But greater than 1. Okay, so here's all my constraints. I'm going to change this. Oh, I don't know why I wanted to run that. Oh God, did I lose it all? I want to change that to 10 just so we know they're all the same. Okay. Okay, so each of these parameters is maxed out at 10, but it has to be at least 1. Okay, so I mean, what do you expect the results to be on this, right? You're trying to minimize. Oh, sorry. We want to keep the inertia, let's say, where it's at, right? So we need another constraint here. So we want the beam inertia to be equal it was 304 before, okay? So we want to keep the same inertia and minimize mass. Now you can over-constrain this and it'll tell you. Like if these constraints don't ever let me get to an inertia that size, it'd be a problem. So I'm gonna hit solve. And it says, the solver found a solution, all constraints and optimization conditions are satisfied. You can keep the solver solution. It actually went and changed it, right? Or I can restore my original values, right? So I'm saying, okay, I'm gonna keep it. So it minimized mass by obviously making the web as tall as it could be, 10 inches, as thin as it could be, 1 inches. And then the flange height, it optimized the flange height to make the 304, right? So once it maxed out on the web, right? If the web could go higher, this would end up being 1 inch, right? All these should be 1 and this should be 10. That'd be the ideal I-beam, right? But the inertia is too low at that point, right? So if I do a different solver, I could make a constraint that says I just want it to be greater. Less than 304. Let's try that. And now it just minimized everything, right? So I basically said, I don't care what the inertia is, right? So it minimized everything. But so you can just set your goals for whatever you want. It's pretty straightforward. Or you could set the objective to maximize inertia, right? I mean,
Maximize inertia to mass.
what do you want to do?
Maximize inertia to mass ratio.
Oh, okay. Oh, okay. So we can do that. You can do inertia divided by, I think you can do, I might have to hit equals. Maybe. And I want to maximize that, right?
No.
Yeah, I'm going to delete this, right? Wait, what did it say? I don't know what it's telling me.
Is that equal sign on the right there?
Oh, it's not like in this? Well, this is what you would do, right? So you just do, this is good, this is, oh my God. I just don't want it to do anything. Okay, I'll just make it a number. Okay, so this is where we're gonna just do this. We're just gonna have you have to do it here. So this is inertia over mass. Okay, so now we'll do the solver, and now we'll make this. Okay, maximize that. Delete this, and solve. So you're making everything 10 and the web thickness 1.
We need to do this for our frame cube.
Yeah, I mean it's straightforward, right? It's pretty cool and it's fast. There's another like simpler version of this. If it's like it's called goal seek. Okay, goal seek. So you want to set like this cell. So let's say you knew everything and you wanted to, let's say this is what you knew already and you wanted to set the web height, right? To have a certain value. So you want to set this cell to, instead of 2175, you want it to be 2100, okay? So, all right, I want to make my inertia 2100 just by changing the web height. There it goes. It changed it to 9.62.
Reverse all of your equations.
Yeah, and you can see it just iterated, right? It's what you would do, right? If you go, let me make it 9, let me make it 9.5, let me make it 9.7. It's just doing that, right? So that's a weaker version of that. You know, it's not an optimizer, but it's pretty useful to do. Like you could do like make my velocity whatever and set and to find out my gear ratio, right? So Excel is super powerful. I mean, and the difference, obviously MATLAB is more powerful, but this is a lot better like user interface, a lot easier to like copy paste stuff, present stuff, right? Like if I wanted to present what I did to you guys, what I did, this is a copy paste, right? If I wanted to show this in MATLAB, right, it would be kind of difficult. And everyone, you can learn Excel easily. Half the stuff I learned in Excel was after school and I Googled it, right? And just played around with it. I mean, I never tried to do a formula and I just learned you can't do a formula in there, right? So Excel is powerful and it's easy to like drag and drop stuff and scroll, you know. So use Excel, you know, in school, like your first 2 or 3 years, you're learning all the hand calc stuff. And then, you know, this is a hand calc. You're using an Excel, but it's a hand calc, right? It doesn't mean you have to get out your engineering paper and write the long things. Once you understand that, you know, don't feel bad using the tools, the Excel and all that, right? I don't hardly ever write out formulas by hand now. I'm always doing stuff in Excel because I know I'm going to want to change something, right? And it's super easy now. Yeah, this actually took me 20, 30 minutes to set up, right? Especially when it's like, why did I pick an I-beam? So now I do the parallaxis theorem, right? As I could have just picked a freaking tube, but I think it helped to actually show the 3 different examples. But I did this, and now actually my uses that work. Now I can change these parameters all I want. And so now, if you want to see where the limit is, like similarly, you could just set this stress. You could use the goal seek, right? And I want to set my stress to be, you know, the yield stress or whatever of some material. Tell me that load will give me that, right? So I could apply a ton of load before I yield this, right? That's because they changed my inertia to some crazy inertia. Now, when you change this, if I recommend you change this, it like undoes the goal seek. Like, this number's not going to change again. You know what I mean? To make this 14 or whatever, you have to always do it again. Same with the solver. Once you input it, it's not running anything anymore. Okay, I think that's all I had. Is there any questions on this stuff or any other different kind of questions? Oh, and there's the export. You can export the report. I think it's just right here, report. And you can decide what you want it to export. I don't know the difference between the publish and apply, but I guess this is going to make it. And then it starts doing this all in Word for you. Now don't take the easy way out and just like I still think you should take this and put it into a PowerPoint where you can describe it a little bit better. It's doing all that. I don't know why it needs to zoom in to do that. It's like the dream sequence. Is it taking snapshots? Yeah. Oh, I don't even know if I should we stop recording the. I guess it doesn't matter.
Yeah, this is good stuff.
So it gave me this. So this is where I copied the. Oh, you can get the section properties here. Remember, the units matter. So I think there's some place to change probably the global units. There's probably even a default that you could change every time you open SolidWorks. It goes to whatever units you're using. But yeah, this was some of the stuff I showed you guys before. So here's a material property. So you can just paste this in there, and it's Word, so you can like edit it too. I don't know if we actually had results on this one manually. Here's where you can check your result in forces. I'm sure there's other ways to do it, right? But you can just check other things out here. Yeah. Oh, there's the sub-modeling thing. There's also a calculator here. There's a way to in SolidWorks to put in like your cross-sectional, like that I-beam. Like you can actually like type that kind of stuff in manually instead of like modeling it, and it'll give you like cross-sectional. It'll give you all the cross-sectional properties. Yeah, so there's a sub-modeling thing you guys should look into, which I don't know if it's a way you do a study. Sub-modeling right here. I don't think this is applicable because I think you need two different parts. I haven't tried this yet, but so here you go. Something can help transfer complex global loads from an entire structure to a local region and attain accurate stress results in that region. Different designs for the regions to help demonstrating. Parent study must have more than one body, right? So they're all meshed as solids. I guess there's some help. You can change it. Anyway, so there's things where you can have the suspension and frame kind of together. Or a good example might be the kingpin with the A-arm. Because like maybe you guys get the forces at that kingpin, and then you attach the A-arm. I would pin it at the frame. Who cares about the frame, right? And then and then do the sub-mod. In fact, you could put the frame in there, but if you just did sub-modeling, it would get the loads at those other bodies and then run an analysis on that. Yeah. Anything else? I know there's a lot to take in, and we lost a lot of people, but it's a complicated topic. I barely broached it, really. I don't consider myself an expert in it. I'm just telling you what I've learned from doing it for a little over 10 years. You know, you hear the term, you like know enough to be dangerous, right? I mean, I think some of the students are dangerous without even knowing enough. So, just be careful. I mean, I said it all in the presentation. So.
That's a lot of questions.
Yeah, I'll put this in Dropbox or something, whatever you want me to do. In fact, I'll save like the inputs that I did here. And yeah, we didn't go back and talk about this, but we kind of talked about the accuracy, right? Like, you know, at least for that specific model, when you was gonna the setup and runtime, I think you can tell from the view it's just like way better, right? And if you can tell on just that little object, you're gonna be able to tell on a frame. I guarantee you save an hour of analysis time if you solid meshed a frame versus did beams. Okay, do not solid mesh your frame. And then how to quickly iterate, right? If you had your frame solid meshed and you go, oh, I want to make all of this tubing 1-inch OD instead, 1.25, you'd go back and edit all your sketches or all your whatevers, right? Where if you're, I mean, I guess you could still do a solid mesh on a weldment, but you know, if you have beams and you're using weldments, it's super simple change, right? And then post-processing info, you saw the difference, right? Solid mesh actually gives you a little bit better info. I could select nodes along the whole thing in the mesh to get stresses, where the beams, that first picture, the whole beam was the same stress, that whole cross-section until we rendered it, right? So just notice you're gonna get different results from different types of running. Yeah, that's all.
Sweet. All right. Thank you.
You can stop your recording?
Yeah.
Okay. I'll stop sharing.